Okay, let's start with our new topic, which is vectors. So, first of all, what is the definition of a vector, and what is the definition of this other term that we use, which is scalar? So, a scalar quantity is a physical quantity that has no sort of sense of direction to it. In other words, if you look at some of the physical quantities that appear down on the bottom of the screen, when we talk about the mass of an object, for example, there's no sense of direction to the mass. So when we have an object, its mass could be 2.3 kilograms, but we would never say that its mass is 2.3 kilograms to the north or 2.3 kilograms at a compass bearing of 210 degrees. That doesn't make any sense when we talk about mass. Mass is simply an intrinsic property of an object, but there's no sense of direction to it. On the other hand, there are a lot of physical quantities that do require a direction in order to specify them completely. And a good example of that we've already dealt with is velocity. So when we say how many meters per second something is traveling, we're giving the magnitude of the velocity, right? Which is the size of the velocity, if you will, or the strength of the velocity. But that is only a partial description of the velocity of an object. If I were to tell you that I saw a UFO in the sky and it appeared to be moving at a speed of 500 meters per second. The next question, then, if I didn't say anything else, the next question you would be asking in your mind is, well, what direction was it traveling? Was it 500 meters per second to the south, or maybe to the east, or maybe straight up? So, in other words, velocity inherently has a sense of direction to it. If you could just mention the number of meters per second, but it's an incomplete description of the full physical quantity. And there are a number of other physical quantities that are this way as well. So please pause the lecture right now and try and identify which of the quantities on this page in this problem that's taken from tutorial 8, which of these are scalar quantities and which of these are vector quantities. Okay, so I hope I'm going to reveal the answers right now, and I hope that this is what you deduced, except for maybe the quantities down here at the bottom that are upcoming, because these are ones that we haven't met yet, right? So these ones here along the bottom, energy, for example, has no sense of direction to it. It's just a quantity. It's an amount of energy. And these other guys, power and momentum, we'll meet them in lectures to come. Of the quantities that we have met already, the ones that have no sense of direction to them include mass, temperature, speed we'll talk about later, but that's true. Remember how speed is equal to distance traveled, which has no sense of direction, right? Distance traveled is distance along whatever path is traveled. But when you say what distance has been traveled, you strip it from of having any sense of direction. You just say, okay, what's the total distance traveled along the path, regardless of what direction the path may have gone. If you want to know what direction an object has gone, then you have to stick with the displacement, for example, right? Acceleration also has a sense of direction always attached to it, as does velocity, like we mentioned before. Time, probably, I mean, for all intents and purposes in this class, time always flows only in one direction, only forward, and always at the same rate. So time is basically a scalar quantity because we'll never have it never has any other direction other than the one direction that it always has. I suppose you could have a philosophical discussion about whether time is really a vector or not, but we'll leave that for the metaphysicists. Now, how do we write a vector? How do we describe a vector? I'm going to go into some detail here because this is something that we're going to use pretty much every lecture for the rest of the semester. So, and Physics 152 as well. So it's important for us to really agree on the notation we use to describe vectors and the terminology. You'll notice that our book is very consistent with this as well. first of all, if we have a vector quantity and we want to describe the full vector, if we want to describe, in other words, both the magnitude and direction, or the equivalent of that would be to provide all of the components of the vector, okay? Then when we talk about the full vector, either in text or in math, then we write, if you're typesetting it, then you write it with a boldface letter. It can be capital or lowercase, that doesn't matter. And A is just some generic quantity that I'm just making up. It could be acceleration, or it could just be something else, some other vector. Okay. So when you're typesetting it, we use a boldface letter. When you're writing it by hand, we write the letter or variable, and then we put a little arrow hat over the top. Okay. That is the way of saying this is the full vector. So that's got to include all of the details of the vector. If you just want to talk about the magnitude of the vector only, and it turns out many of our equations are going to just need the magnitude of a vector, then the way to do that is to write just the letter without a vector hat on top. Now, there's a longer way to do it, which is what you'll see in most mathematics textbooks, which is to write it with a double bar on either side, or even a single bar on either side, which looks like absolute value. But that's what absolute value is. Absolute value is the magnitude of a number on the one-dimensional number line. But normally, though, what you'll see is both in regular writing and in formulas, people won't bother to write quite so much. This is very laborious to write the magnitude of every vector as the double bar on either side of something with a vector hat. So we only use that notation when we have to be extra explicit. Otherwise, you'll just see us write the letter by itself, the variable letter all by itself. So basically, the most common ones you're going to see then are when you're writing by hand, you're going to use this notation to mean the whole vector, and you're just going to use the letter by itself without the vector hat on it to mean just the magnitude only. When you want to write the direction, then, well, you can use if there's no other qualifiers on a angular direction. In other words, if I don't add any additional words that say above the horizontal or to the west of south or something like that, if it's just degrees, then you can assume that it is the so-called trigonometric direction. Meaning, if we were to take this vector and pick it up and move it over to the origin so that its tail sits at the origin, like this. So here's the origin right here, and the tail is at the origin. This is the positive x direction, that's the positive y direction. Then what do we mean by the trig direction, right? The trigonometric direction, also known as the trigonometric angle or the proper angle. Well, it's generally, one way to define it is to say that it is the number of degrees measured counterclockwise from the positive x direction. Really, technically, mathematically, it's really the number of degrees measured from the positive x direction through the positive y direction. But that will virtually always be counterclockwise for 99% of the times that we draw axes on any of our physics problems. So we won't worry about for now, we won't worry about the very rare cases when the positive y-axis is flipped and is on the other side from the positive x direction. Instead, what we've drawn here is what we call in math is called a right-handed coordinate system. So as you curl you could take your right hand fingers and curl them from X toward Y, and Z will point out of the page. And that's what we will almost always be drawing. So in that case, following what we learned in trig class, we would start at the positive X axis, and we would then measure our angle counterclockwise from there. So this would be the trigonometric angle or trigonometric direction for vector A. Okay. So even our textbook says counterclockwise from the positive x direction. What if we went the other way around? Well, then technically that is going to be negative of the trig angle. But sometimes the negative angle is convenient to use, especially when you're down here in quadrant number 4. So if you're over here in the 4th quadrant, negative angles are often more convenient than writing out a big trigonometric angle with 300 and some degrees. right? But when you're in quadrants 1 or 2 or 3, it's usually the case that it's more convenient to use the positive trig angle. So instead of going in the negative clockwise direction, we'll usually stick with the positive counterclockwise direction. Now you'll notice I started off this whole description by saying, what if we were to take the vector, pick it up, and move it over so that its tail is at the origin? Well, remember, what is it that defines a vector? It only has two components, really. It has a magnitude and it has a direction. So as long as you preserve those two things, as long as you keep those two things constant and unchanged, you don't change the nature or identity of the vector. There's nothing in this description here between magnitude and direction that says where the vector needs to be located in space or rooted in space. In other words, this is independent of origin, of our choice of origin. So we could take a vector, and as long as we carefully maintain its magnitude, as long as we carefully maintain its direction or orientation, we can then slide it around in space. We can translate it, in other words, is a fancier way of putting that. We can translate it we can slide it around as long as we don't stretch it and as long as we don't rotate it. Okay, those are the two things that we're not allowed to do. But translation is just fine. So you're always allowed to take a vector, pick it up, and slide it over so that its tail is at the origin. And then you can see, oh, at what Cartesian coordinate does the tip of the vector lie at? And we're going to learn to think of that as a vector component. Now, before we do that, let's talk just a little bit more about other ways of denoting direction. So what we've described so far is if you were to take this vector, put its tail at the origin, and then take the angle counterclockwise from the positive x direction. We're going to call that the trig direction or trig angle. That's what I'll usually call that most of the time. Are there other ways to denote the direction of this vector? Yes, there are. Turns out that you can come up with sort of a custom description, like degrees above the horizontal. That's something that we use a lot when we're talking about the direction that something is launched at, or degrees to the right of the vertical or to the left of the vertical, or degrees below the horizontal, or any other sort of, when you have some sort of fiducial reference, you can talk about angular directions with respect to that fiducial direction. However, there's a really common one that's used for bird's eye views, in other words, top views of situations, and that is compass bearing. So if you imagine that we were to define, let's say, let's suppose vector A here is the displacement along the ground. Okay, it is a displacement, pardon me, along the ground. In other words, and then this might be a top view of the situation right now. In other words, a bird's eye view of the situation. Then what we can do is we can choose our x and y directions to lie along two of the cardinal compass directions. And the ones that we're going to use the most often are going to be east and north. And in that case, sailors, hikers, pilots, soldiers, people who use compasses or who refer to directions of things on the surface of the earth by compass directions, they use a custom where they measure the angular direction starting from north and going through east. So unlike what's drawn here in yellow for the trig direction, the compass bearing starts from north. Okay, so it starts from this direction, and then it's measured through east. So put another way, we would start here at north, and we would go through east and go all the way around the other direction. That number of degrees right there is the compass bearing. I'm going to use phi for that, although phi is not like a standard variable. It's used widely. I'm just going to use it to distinguish that from theta. Okay. So in this particular example, it looks like the compass bearing is very roughly like 325 degrees, give or take, right? So one sailor would say to another sailor, this vector has a bearing of 325. All right, so that's going to be commonly used as well. Now the final thing that we'll talk about with vector notation is how to denote and write components. So let's consider this same like generic vector here, vector A, okay? And again, let's pick it up and move it over so that its tail is at the origin. And what we're going to do now is we're going to say, okay, once we've slid this vector over to the origin, look at where the tip of the vector lies in space. So we're going to ask, what are the Cartesian coordinates of that point in space? Now, on my screen, and for most of the vectors we're using right now, there's only 2 dimensions, right? When we get into physics 152, eventually we'll have 3-dimensional vectors when we start talking about magnetic fields. But otherwise, even though vectors, even though most of our physical problems exist in 3D space, we can usually define the plane of our page or the plane of our screen or our chalkboard to be the plane of motion. Like if we launch something in through space, we will have the plane of our page um, or the screen, the computer, be the plane in which it is traveling. And that removes the need to deal with a third dimension or to deal with the z direction. So we'll always choose that to make our math as simple as possible. So we're usually going to collapse all these problems to 2 dimensions. So now let's ask ourselves the question, okay, what are the x and y coordinates of this point where the tip of the vector lies? So we're going to call the x coordinate a sub x, and that will be the x component of the vector A. And we'll call the y coordinate a sub y, and that'll be the y component of vector A. And again, I'm just going to do 2-dimensional for now. Another thing that those coordinates represent is they also represent the length of the quote unquote shadow that that vector casts onto the x direction, the x axis, or onto the y axis. So sort of the more mathy term for describing this shadow would be the projection. What's the projection of the vector onto the x-axis and the projection onto the y-axis? Well, let's do the x-axis first. If we were to shine a spotlight from high above so that the shadow of vector A falls onto the x-axis, then we could say, oh, this is what the projection looks like on the x-axis. Notice how the projection is shorter than the full vector, right? It's always going to be either the same length or shorter. It'll never be longer. So right here, this negative value right here is, of course, the value a sub x or the x component, which in this case is negative because it lies in the negative x direction, right? Or you could also say that this whole thing here is the x component or the x component vector. So this whole, sometimes you'll see me label it like that, or sometimes you could think of a sub x as also just being this x value right here. Same thing for the projection onto the y-axis. So the y component is right here, right? Or you could think of this as being the y component as well. Right, so either way you think about this, though that's what the components represent. You could think of them as representing the Cartesian coordinates of the point where the tip of the vector lies if the tail is at the origin, which is very important. Or you could think of them if the tail is at the origin, what is the projection of this vector onto hypotenuse of the y-axis? Once you know what the components are, then there are 3 common ways to write this vector in component notation. The one that you're going to see me using a lot in both typing and handwriting is this first ordered pair notation. And the reason is because it's just really convenient and quick and easy to write little parentheses on either side. There's a more laborious way to write, and by the way, this is what it looks like in 3 dimensions, and then that's what it is in 2 dimensions. There's a more laborious way to write this when you're typing, but it's just as fast when you're writing by hand, and that is to take the x component and multiply it or use it like a coefficient that's multiplied against this little unit vector abbreviation. And you'll see I with a little hat on top or X with a little hat on top to mean the unit vector along the X axis. J or Y means the unit vector along the Y axis, and then K or Z means the unit vector along the z-axis. So the way you write components in this case is you write it as this coefficient times the unit vector, this coefficient times unit vector. Okay? And you don't need parentheses. I put parentheses on here a little bit by accident. You don't need these parentheses unless they're necessary for clarity around the individual coefficients, because let's say there's units, right? And there's too many. If you're writing a complicated number value here with powers of 10 notation, units and everything, then sometimes we'll put parentheses just around it before the I hat or the J hat, just for extra clarity. But otherwise, those parentheses are not normally needed. All right, so I hat and J hat, X hat, Y hat notation is very common. You might see it in your lab manual. You might see it in a number of textbooks. Just for convenience, I'm probably going to use the ordered pair notation most often. But don't confuse an actual Cartesian point in space with a vector. Okay, all we're saying is that if you put the tail of the vector at the origin, this point is where the tip or head of the vector would lie. All right, let's look at a couple examples of what it looks like when we write a vector in these forms. So here's a sample vector. This vector is for an initial velocity of a soccer ball. So suppose that I were to tell you that this vector has a magnitude of 35 meters per second at a direction of 40 degrees above the horizontal. Okay. So in that case, I can say, all right, let's draw the positive x-axis along the horizontal. In that case, 40 degrees above the horizontal turns out to look like this. And then I could draw my vector. I label it with v naught. And I can see by inspection that the trig direction is naturally given in this direction, counterclockwise from the positive x-axis. Oh, that actually matches above the horizontal. So in this particular case, the trig direction is the number of degrees above the horizontal, and no further conversion is necessary. That's not always going to be the case. Sometimes, if this is kicked to the left, for example, 40 degrees above the horizontal would not be the trig direction. The trig direction would be over here on the other side. It'd be 140 degrees. Okay? But in this case, if I choose my positive x direction to be downrange in the direction that the soccer ball is kicked, then the number of degrees above the horizontal is exactly the trig direction. Okay? What's the compass bearing of this ball? Well, it's not really appropriate to put that on this diagram because this is a side view of the situation. In other words, you can imagine a person standing right here and that the soccer ball is right there. Okay, well then what direction is north on this little drawing or diagram? Well, we don't know. It's not specified. Is it the positive y direction? No, that's not north. That's upward. That's away from the center of the earth. Right? And down on this diagram is not south. Down on this diagram is toward the center of the earth. So this is downward. Unless there's more information that says the soccer ball is kicked due west or something, right? Or due north, then we might be able to give plus x, positive x here, some sort of a compass direction. But otherwise, it's not appropriate in this particular case to, just because you see a couple of axes, a pair of axes, it's not appropriate to just suddenly slap the term east on this one that's to the right, or slap the term north on the one that is toward the top of the page. That is inappropriate in this case, and it doesn't make any physical sense, right? In this case, toward the top of the page is in fact upward. So only use compass bearings or compass headings if it is a bird's eye view or top view of a situation. However, this is a side view. You could also write the same vector in components in ordered pair notation, like I have here, or in I hat, J hat, or X hat, Y hat notation. And in that case, that means if we were to put the tail at the origin, the tip would appear to be at the X component, comma, Y component location, or you could say the projection of this vector onto the X axis or on the y-axis are equal to those two components. Notice in this case, all of the components are positive. So even if I didn't have a drawing over here, even if my drawing were not provided, and if you were to hide the drawing on the right-hand side of this slide, just by looking at these components here, look at their plus and minus sign, right? Notice that all of these components are all positive, or both the components are both positive. So that tells me that my vector must lie in quadrant number 1. If the x component were negative, then that means it would lie in quadrant 2. If both components are negative, it'd be down in quadrant 3. And if only the y component were negative, we would be down in quadrant 4. So even if there were no drawing here, no sketch, you can tell which quadrant your vector lies in just by looking at the plus or minus signs on the components. This is going to be really important for the inverse trig functions that I'm going to talk about in a couple more slides. Let's look at just one more example. What I'm going to do now is suppose that a little gecko undergoes a displacement of 2.3 meters at a direction of 250 degrees. Now, if I don't have any qualifiers after 250, if I don't say to the east of south or a number of degrees below the horizontal or something like that, then it's safe for you to assume that this is the trigonometric direction. And so in this case, 250 is just the trig direction. Okay. What I'd like you to do is try to, first of all, looking at the information given here, try to predict which quadrant this vector is in. If it helps, you can look at the components down there as well. Try and predict which quadrant the vector lies in, and then sketch the vector on these axes that are provided right here. So press pause now, and after you've sketched the vector, then continue with the lecture. Okay, I hope that you drew something along the lines of this vector right here. Notice that it lies in the third quadrant, and notice how the 250 degrees is getting pretty close to 270 degrees, right? And 270 would be down here in the negative y direction. So you should definitely be closer to the negative y-axis than to the negative x-axis. Also, another way to verify that is notice how the y component is much larger in size than the x component. So that means that this vector needs to have a much bigger y component than x component. So it would not be accurate or good for you to have sketched the vector just sticking out at sort of a 45-ish angle in the middle of quadrant 3. And it would in fact be even worse if you had sketched it down over in that direction of quadrant 3. Right? To make the sketch realistic at all, you should have it pointed sort of toward closer to the negative y direction. Okay. I want to mention one more thing about compass directions. Now, in this particular case, this in fact is a sort of top view or bird's eye view of a situation. So if a little gecko starts here at the origin and undergoes some displacement. Now, we're not told whether that gecko travels in a perfectly straight line or if actually the gecko's path is something more complicated. And just at the end of some time interval, the gecko winds up at this location here. Then that means that the total displacement of the gecko is vector s over some time interval that's not specified here. Okay, this is a bird's eye view or a top view. And in that case, if we wanted to, we could define one of the directions along east and the other one along north, and we could convert the trig direction to a compass bearing. Okay, now just to be safe, you'd have to be told that positive x is east and positive y is north, and then the compass bearing can be deduced as the number of degrees. Do you remember how to get the compass bearing? It's the number of degrees from north through east. So that's drawn here in purple on the diagram, and it's 200 degrees. There are a couple of other compass-like directions that you're likely to see. Let me clean up the diagram slightly. Okay, and those are shown, those are written here in purple, which is when you have a vector that lies in a particular quadrant, like this one. This one lies in the third quadrant. That is between west and south. So what that means is, instead of giving the full compass bearing, which is degrees from north through east, which is 200 degrees, it's also likely that people would prefer to give instead the number of degrees away from the nearest cardinal compass direction. So notice that from west, you would go 70 degrees south of west, and that would also give you the direction of S. Or you could go 20 degrees to the west of south, and that would also give you the direction of vector S. So in our textbook and in problems on Mastering Physics, you're going to be likely to see problems that say 20 degrees to the, and sometimes they'll just use these little abbreviations, to the west of south, or or even simpler, 20 degrees west of south. Okay, or 70 degrees south of west. And again, you always choose the two compass cardinal directions that are closest to the direction you're talking about. And of course, if a vector lies exactly along a cardinal direction, then you just say due west, due south, due southwest. Okay, but that you should only use those terms when it's exact, due north, right, or due northeast. Now, suppose the last slide we have coming up of theory is, suppose that you know the components of a vector and you want to find the magnitude and direction, or conversely, suppose that you know the magnitude and direction and you want to find the components. Well, what we can do is we can note that when we look at a vector and its components, notice how the vector itself and the components always form a sort of a right triangle with each other. So that means that we can take that right triangle and we can perform simple geometry or trigonometry on it and come up with some conversion equations that allow us to relate the sides of that right triangle to each other and to the interior angles. So I'm going to stick with just the trig direction angle, okay, which is the one here close to the origin, always measured from counterclockwise from X through Y, okay? In that case, if you follow these equations that are written here, sometimes when theta is bigger than 90 degrees, when the trig angle is out beyond 90 degrees, then the cosine or the sine could be negative. In that case, you'll get a negative value for the X component and or the Y component. That's okay. In fact, that's desirable. These formulas will consistently give you the correct plus or minus signs on our X and Y components, as long as you always plug in only the trig direction angle to these formulas. If you're used to crafting your own triangle with a vector, like let's say you took physics in high school before, and when you have a vector that points off in some other direction, some of you may already be comfortable with sort of saying, okay, this is the X component and that's the Y component, and I'm going to use this angle right here, alpha, or that angle up there, beta, because that's what's given in the problem. Or maybe it's just convenient, and it's a nice convenient small angle, as opposed to always saying, well, this is the trig angle right here for the vector that we want. If you want to rewrite these equations in terms of alpha or beta, then that's just fine. If you're comfortable with your trigonometry and your sort of your bookkeeping skills for the plus and minus signs, you're welcome to sort of come up with your own triangle and devise your own formulas that work for that particular vector in that particular problem. However, that there are too many possibilities to consider all of those, or for me to show those as examples in solutions that I'm posting for tutorial problems. So I am just going to always stick only with the trig direction angle. And you can brew your own sort of triangles, but do so at your own risk, okay? So sticking with the trig direction angles then, these formulas here will always allow you to convert from trig direction and magnitude into components, or vice versa. If you have components, you can always get magnitude and direction. The first three of these formulas are pretty simple and straightforward and easy to use, and you'll recognize them as SOHCAHTOA and Pythagorean theorem. The fourth one is SOHCAHTOA also. This is the TOA part for tangent, but there's sort of a caveat to worry about, and that is when you take inverse tangent, when you take the inverse tangent function on your calculator, every calculator I've ever seen will only show you one of the two solutions for inverse tangent that exist on the unit circle between 0 and 360 degrees, or between 0 and 2 pi. And the other solution is left for you to figure out on your own. Okay? So if that's true for the calculator that you're using, then at least for arctangent, and this is not true for arcsine or arccosine, but for arctangent, the second solution that your calculator is not telling you, you can easily find by simply adding 180 degrees or subtracting 180 degrees from the solution that's on your calculator screen. By the way, adding 180 and subtracting 180 are the same thing because they are 360 degrees apart from each other. And as you know, on the unit circle, when you add 360, you're back to the exact same direction or same angle. So take the value that you get on your calculator screen, add 180, or if the numbers are getting too big, try subtracting 180 instead. It's fine if the initial value is negative. That's all right. So same thing. Then now you have a second solution. Look at the original solution on your calculator screen and the second solution, identify what quadrants they are in, and figure out what quadrant the answer for your direction should be in. Now, if you happen to have a sketch, you can just do it by inspection and look at it and say, oh, that vector lies in the first quadrant. But remember what I said before, if you don't have a sketch handy, and or if it would be really complicated to make such a sketch, then you have to look at the plus or minus signs of the two components. If the two components themselves are both positive, then you know that you're in the first quadrant. If one of them's negative, then you know you're in either the second or the fourth quadrant. And if they're both negative, then you know you're in the third quadrant. So look at the plus or minus signs that sit on your components, and that will tell you which quadrant the answer should be in. Then you're almost done. Keep the solution, keep the one of the two angular directions that is in the quadrant you want, and the other one, which will be 2 quadrants away, throw it out and just discard it, and then you're done. This sounds complicated, but after you've done it a few times, it gets pretty quick and efficient. Okay. So this is our theory. Memorize these 4 equations here. Of course, they are just SOHCAHTOA and Pythagorean theorem. So I know that you already know the math, but this is just, I sort of have memorized these equations along with a simple sketch like that, where I just draw a generic vector, and I draw the x component and the y component over here on the right. I just move it over there. And then here's the trig angle, and it's very easy for me to rederive these formulas just using SOHCAHTOA and Pythagorean theorem. So if you don't remember exactly which one's which, then just sketch the vector and its 2 components, sketch the right triangle, and remember your geometry and trig. And you can always rederive these. Let's do 2 examples from tutorial number 8, question 4 and question 5. And then I'll leave 6, 7, and 8 for you to try on your own if you'd like additional practice. Okay, so starting off, suppose that you have a displacement vector and you're given, for problem 4, you're given its magnitude and its direction. So the magnitude is 44 meters and the direction is the trig direction. is 120. And remember, if I just give you a direction with no further explanation or qualifiers, you can assume it's a trig direction. All right, so what we're asked to do here is to find the x and y components of this vector, find the compass bearing of this vector, and before all that, we can make a sketch, okay? All right, well, first of all, think what direction is 120 degrees while I draw my axes here. Okay, so a trig direction of 120 degrees would mean I start here, the positive x direction, and I go counterclockwise by 120 degrees. So that means that my vector should lie over here somewhere. Oops, that pen didn't work. Should lie over here somewhere. Okay, so this is my vector d. I think I need a thinner pen. Okay. And I can already sketch what the components should sort of look like on this sketch. This should be the x component, and that should be the y component. Now, this is actually pretty useful for me now because this is going to give me a sanity check. Notice that my y component, when I'm all done calculating it using my formulas, my y component should be positive, my x component should be negative, right? It also looks like if my sketch is good, the y component should be a little bigger size than the x component as well. All right, so now we can calculate what these should be. X component of any vector is equal to the magnitude of the vector times cosine of the trig angle. So that's equal to 44 meters times cosine of 120 degrees. Now again, if you weren't given the trig direction, if we were given some other wacky direction, like the 60 over here or something, then we would need to find the trig direction in order for this formula to always work, 100% of the time and give us the correct plus and minus signs on everything. So that turns out to be negative 22 meters. Y component, magnitude times sine of 120 degrees, and that turns out to be positive 38.1 meters. Okay. So if I want, I can write this in a number of notations. One notation would be ordered pair. Remember, when I put the hat on the vector, that means I'm about to write the full vector. So I'm going to write either the magnitude and direction, or I'm going to write all the components. So this time I'm going to write all the components, negative 22 meters, positive 38.1 meters. Now you never need to write the plus sign. I'm just doing it here for emphasis. Or if I want, I can write it as I hat, j hat, or x hat, y hat notation. Negative 22 meters times I hat. I guess I don't really need the parentheses. Well, okay, I will keep the parentheses on just so it's clear that the meters belongs to the coefficient. Plus 38.1 meters times j hat. Notice in the upper, I'm just going to make a point here really fast. When I use the component, when I use the ordered pair notation, you use a comma in between the two to separate them. But when you're using this I hat, j hat, or x hat, y hat notation, then you don't use a comma. Instead, you use a plus sign or a minus sign. X hat plus 38.1 y hat, okay? So there's no comma at all, okay? Finally, compass bearing. Okay, there's there's no really easy formula that says compass bearing is equal to, trig angle plus some number. You can come up with a formula like that, but I think it's better and easier for you to just look at the problem and try and figure it out on a case-by-case basis. So what you should remember is that compass bearing, it starts north and goes through east. So we're going to start at north and go through east. and go all the way around until we hit the vector. So in that case, we see that this is 90 degrees plus 90 plus 90 plus 60. So in that case, the compass bearing turns out to be 330 degrees. All right, let's try problem 5. And problem 5 is another displacement vector, only now I've just reversed things. In this case, I'm giving you the components, and I'm asking you to find for me, so here are the components here, I'm asking you to find for me the magnitude, the trig direction, and then the compass bearing. And a good way to start, again, is to have a little sketch which gives us a sort of sanity check. All right, so I recommend, if you're comfortable at this point, and you can do this on your own, at least pause and at least make the sketch, just based on these components that you have right here. Okay? If you can proceed to get the magnitude and direction and compass bearing, go ahead and do that too. And then unpause, and you can compare with my answer. Okay, so let's go ahead and create our axes. Positive y, positive x, and I can see that this vector here has positive x component and a negative y component. So that means I'm going to be in quadrant 4 down here, and I can. It looks like the x component is a little bigger than the y component. So I'm going to guess that it means that my vector is going to be a little closer. Oops. Oh, oops. It looks like that means my vector is going to be a little closer to the x axis than to the y axis, right? Because that means that the x component is a little bigger than the y component. So if I, in other words, put another way, if I were to sketch, if this is the vector r, then this could be the x component, and that could be the y component, right? There we go. All right. So notice how my x component has more meters in it or kilometers in it than my y component does. Okay. Where's the trig angle on this graph, on this sketch? Well, it looks like the trig angle, I can draw one of two ways. The positive trig angle goes from positive x counterclockwise through positive y. So theta sub r could be that way. Another way to draw it would be here, and I'm going to write it as negative theta sub r, okay? Because that's going clockwise. So that means that however many degrees that is, I should write it as a negative quantity. Okay. All right. So let's go ahead and find the magnitude. The magnitude of r is equal to that Pythagorean theorem formula, 5.8 kilometers squared plus, now the y component is negative 3.4 kilometers, but when I take that square, the minus sign ends up squaring away, and I get that the final answer is about 6.72 or about 6.7 kilometers, okay? To just two significant figures. Actually, I'll just, yeah, that's fine. But the final answer is 2 sig figs. What about the direction? So the trig direction we can get from our TOA formula, right? Inverse tangent of the y component over the x component. So that's equal to inverse tangent of negative 3.4 kilometers over positive, over positive 5.8 kilometers. Now, just as a little double check, notice how I'm carrying all my units around with me. Notice how the units will cancel, leaving this as a dimensionless quantity for the inverse tangent, which is very important, right? So remember, inverse trig functions, you need to feed them dimensionless quantities, and then we get out an angular quantity. So if my calculator is set to degrees, then this will be the inverse tangent of, sorry, I didn't leave enough room, negative 0.586. And my calculator tells me that answer is negative 30.38 degrees. Now, what my calculator is not telling me is the other solution. So I know that if I either add 180 or subtract 180 from this, I will get the other solution on the unit circle. So I add 180 and I get 149.62 degrees. Now, only one of these is physically the correct answer, the correct direction for vector r, right? The other one is opposite to the correct direction for vector r. So which one's correct? Well, let's identify the quadrants of both of these. I know that this angle, this trig angle, is down in quadrant 4, right? It's about 30 degrees down from the positive x direction, whereas the other one is over in quadrant 2. It's up there. It's 149 degrees counterclockwise, so this is in quadrant 2. I know from my sketch already that the quadrant I want is quadrant 4, or I'd look at my positive and minus signs that are on the two components, and I would deduce again quadrant 4. So this is the answer that I want, and I discard the other one. So just rounding that off to maybe to the nearest degree. Sig figs are weird with angles. So, you know, if you were to leave this as -3.4, that'd be fine. Or I've rounded off all the answers here just to the nearest 1 degree. So it's -30. Remember, 360, adding 360 degrees or subtracting 360 degrees from an angle doesn't change the direction of that angle on the unit circle. So negative 30 degrees is the same as positive 330. Those are the exact same direction. Those aren't opposite each other. Those are the same direction as each other. Opposite to them would be 150 degrees. What's the compass bearing of this particular case? I'm sorry, this diagram's a little messy already. Okay. The compass bearing, do you remember what the definition is? Start at north, and in this case, let's define positive y to be north and positive x to be east. Start at north and then head toward east and go through east if necessary. So it looks like that is the compass bearing. So I can just see by inspection that that's going to be equal to 90 degrees up in quadrant 1 plus the absolute value here of this small negative angle, -30 degrees. So it's equal to 90 plus the absolute value of -30, which is 120. All right. At this point, I'm going to leave the remaining questions, 6, 7, and 8 to you for further practice as you wish. If you already have the hang of this, please go and work on the credit problems on online homework number 8. And we'll pick up with, and online homework 8 is not that long. It's fairly short. And we'll pick up with more vector arithmetic in the next lecture, in lecture number 9.